Right, here's some solutions to some of the electromagnetic induction questions. Right, this one. State Faraday's law. Induced EMF is proportional to the rate of change of flux linkage. 2 marks. Show that the total flux linkage for the coil at time equals 0.4 seconds is 0.45 milliweber turns. Well, we can read off the flux density at that time. 1.3 millitesla. Flux linkage given by n phi being flux, so nba. The cos theta bit I don't need to worry about because the angle is 0 degrees to the normal of that area. 150 turns times by the 1.3 millitesla times by the area of the coil, which is here. Does indeed give you 0.45 milliweber turns. Calculate the induced EMF of the coil between 0 and 0.4 seconds. Induced EMF is equal to the change in flux linkage over the change in time. I think I've made a small boo-boo there. 0.45 times 10 to the minus 3 over 0.4 is 1.13 millivolts. I think I just made a boo-boo on that bit. I think the answer's fine. Explain why the induced EMF in the coil is 0 between 0.4 and 0.6. Well, there's no change in flux linkage. You need the flux linkage to change to give you an EMF. Right, this bit, actually you don't need to worry about this on our spec, but I'll have a look at it anyway. So this is a transformer. Oh, it says so there. Right, this bit here, it acts like a solenoid. There's going to be current passing through there. It's a coil of wire with 9 core. Acts like a solenoid. Don't get any marks for that, but that's what's going on. It's an AC current, so there's a varying current, so there's a varying flux, which passes to the secondary coil through the iron core. So the flux produced here, when the magnetic field is induced, is transferred to that. So there's a changing flux linked with this coil. The rate of change of flux linkage in the secondary coil, so there's an EMF induced. Bish bash bosh. It saves. Right, this question here. Right. Why? Hang on. Explain briefly why an induced current flows through the resistor. The area here changes. As this slides along, that area gets bigger. The area changes, so flux changes. There's an EMF induced, and there's a complete circuit, so current can flow. So current can flow round there. Calculate the current flowing through the resistor. Well, rate of change of flux linkage, I could write that like this. Bn, they're constants. The length of that wire is constant. And I've just times it by delta x over delta t, the change in this length per second. Well, that bit there, L delta x over delta t, is the area per second. And delta x over delta t is the 34 meters per second. So it's just the same as BLV, basically, because n is 1. You should get 1.59 times 10 to the minus 3 volts. V over R is I. So we should be able to work out the current now. Right, students suggest that this current will provide a force on the metal conductor that increases the speed of the conductor. Explain whether or not the student is correct. Like most of these questions, the student is of course wrong. Well, Lenz's law says the force should oppose the motion. No 1 mark, some mention of Lenz's law, and that Lenz's law said there's some opposition there. Now we can actually find out what's going on here in a bit more detail. This wire is going that way. It needs to feel a force that way, according to Lenz's law, for the idea of opposition. As soon as a current flows through this, you've got a current carrying wire in a magnetic field, so it will feel a force. If we use Fleming's left-hand rule, and I'll try and do that, this is a bit awkward. Force, field, current. Well, the field is coming towards you. If the current's going that way, the force will be to the left. Field out, current down through the bowled wire, force left. So actually, you would find the current would be flowing around that loop that way to provide a force that way on that wire. Right, that'll do for this video. I'll give you another one in a second.